Good day, students. So let's do today the last topic of our crash course, that is nuclear physics. Okay, nuclear physics. So in nuclear physics, we are going to talk about nucleus, right? So in nucleus, if suppose I take this is our nucleus. So inside nucleus there are two particles, neutron and proton. Okay, there is proton as well as neutron. Right? We know atomic number. Atomic number is what? Atomic number is number of protons. Number of protons in the nucleus. Number of protons inside nucleus. Okay. And another term is mass number. Mass number means is total number of particles inside nucleus. Okay. Total particles. Total particles or all particles inside nucleus. That means this mass number is total number of protons plus total number of neutrons. We represent mass number with A and we represent atomic number with Z. So A is what here? A is Z. A equal to Z plus number of neutrons. Okay, so number of neutrons means what? A minus Z. Sometimes question is asked on this also. Okay, so number of neutrons is equal to A minus Z. Okay, what about the mass of proton and mass of neutron? Almost same. Okay, mass of proton is 1.672 into 10 to the power minus 27 kg, and mass of neutron is 1.675 into 10 to the power minus 27 kg. Almost same. Okay, what about radius of this nucleus? What is this going to be? So radius of the nucleus is given by a relation that we have, R equal to R naught A to the power 1 by. A is what? Mass number. And what is R naught here? R naught's value is 1.2 into 10 to the power minus 15 meters, or 1.2 Fermi. Okay, then what about the density of this nucleus? Now density of the nucleus doesn't depend on the element. It doesn't depend on atomic number, it doesn't depend on mass number. Okay, so density of nucleus is approximately 10 to the power 17 kg per meter. And as I told you, it doesn't depend on which element we are talking. For all the elements, density of the nucleus is constant. Okay. Rho is independent of atomic number or mass number. Atomic number or mass number. What is the meaning of that? It means it's constant. Density is constant. Okay, this is the basic, very basic information about a nucleus. Right. Based on this also, as I told you that they can ask you directly what is the number of neutrons in the nucleus. They will give you Z, they will give you A. Okay. They can ask you about density. They can ask you about this radius. Now see that next question that we are going to do, that is on radius only. Okay, see now what it is. The ratio of radii of two nuclei having mass number 8 and 27. Ratio of radii of two nuclei. Okay. So we already know radius is R equal to R naught A to the power 1 by 3. Now R naught is constant. That is same for all, right? So R1 by R2, we can write as A1 by A2 to the power 1 by 3. Right or not? And mass number means is A only. This is mass number. So R1 by R2 equal to 8 by 27 to the power 1 by 3. Now what is 8? This is 2 cube and 27 is 3 cube to the power 1 by 3. That means 2 by 3. So ratio of radii of two elements which are having mass number 8 and 27 is 2 by 3. Okay. Alright. Then what next is? This is formation of nucleus. Now inside nucleus is what? Neutron and proton. So neutron and proton together we call them as nucleons. Nucleons. Okay. So nucleus is made from nucleons. What are nucleons? Neutron and proton. But what is observed or what is formed or what is found that mass of the nucleus actually is less than the mass of nucleons. That means mass of neutron, mass of proton if you do, and you find the mass of nucleus, you will find that mass of nucleus is less than that. Okay, what we have found? Mass of nucleus is less than mass of nucleons. Okay, so this difference between the masses is called as mass defect. Okay, what is mass defect? Mass of nucleons minus mass of nucleus. Mass defect is equal to mass of nucleons minus mass of nucleus. Now question is where it is gone. Where is this mass is gone? You brought a neutron, you brought a proton and you made them together and you are finding then when you are making them together this mass has become less than the individual masses of that neutron and proton. So where is that mass? So that mass actually according to Einstein energy equation is converted into energy. Okay. So Einstein equation says this mass defect, if I say that this is delta M, okay. Einstein energy equation says that this mass is converted into energy and that is equal to what? Delta M into C square. And this we call as binding energy. What we are calling as binding energy. That means this is the energy which is actually released. When you are bringing these two particles together, mass became less. So where is that mass gone? Converted into energy. So this energy basically is binding these nucleons together. So we said that this is binding energy. This actually is binding energy. Okay, and what this binding energy is? This is binding. We are going to write over there. This is the energy which binds these nucleons together. Okay, right here. Energy that binds nucleons together. Okay, so what this binding energy basically is, as I said, mass of nucleons minus mass of nucleons minus mass of nucleus, not nucleons minus nucleus. Okay, mass of nucleons minus mass of nucleus. Okay, now suppose that we take one small nucleus over here and try and understand. Okay, this is the nuclei. Okay, how many protons are there? Z protons. Or we write, instead of writing this, just take the element. Okay, we are taking an element which is like this, Z, X, A. So element is X, atomic number Z, mass number A. Okay, we are going to talk about this one. Now, what we know is mass of proton. So how many protons are there? Z. So Z into mass of proton plus A minus Z mass of neutron minus mass of nucleus. X is the element. So mass of nucleus into C squared. This is binding energy. This is binding energy. Okay, but mass of proton is huge or very less? Very less. Neutron's mass less, and even nucleus mass is also less. So this mass defect comes out to be very, very less. Okay, like we know that mass of proton 1.67 to 10 to the power minus 27. This is 1.67 to 10 to the power minus 1675 into 10 to the power minus 27. So it will be very less. And even c square, when you do 3 into 10 to the power 8 whole square, still value is very less. So what it was told that why don't we have another unit, why kg and all that. Let's have another unit, AMU, atomic mass unit. Okay, then everything you represent in terms of AMU. What is this AMU? See, AMU. Okay, now AMU's definition was given as it is actually 1/12 of the mass of one carbon atom. That much only I am writing, not more than that. Okay, 1/12 of mass of one carbon atom. Okay, but its value comes out to be what? Almost equal to the mass of proton or neutron. Okay, so 1 AMU is actually equal to mass of proton, that is 1.67 into 10 to the power minus 27. But only thing is, now in place of writing 1.67 to 10 to the power minus 27, I will write it in AMU. Okay, so this is certain AMUs, this is certain AMU, and this is also in certain AMUs. Okay, so binding energy now, suppose that mass defect itself is 1 AMU, then how much is the binding energy? Okay, let's see. So binding energy corresponding to 1 AMU, so 1 AMU, that is 1.67 into 10 to the power minus 27 kg into c square, right? Into c square. This comes out to be what? The binding energy corresponding to 1 AMU. We should not write like this. 1 AMU if I write, okay, 1.67 into 10 to the power minus 27 into c square, that is 3 into 10 to the power 8 square. Something will come in Joule, certain values in Joule. But when we are going to convert this in mega electron volt, because this is very less. So when we convert this into mega electron volt, it comes out to be 931 mega electron volt. So we say that if 1 AMU is the mass defect, then the corresponding energy in mega electron volt is 931 MeV. Okay, 931 MeV. Okay, what happened here? Okay, this is not getting selected. Okay, come on. Right. Okay, so for 1 AMU, binding energy value is 931 MeV. So if mass defect is 1 AMU, binding energy 931 MeV. Fine, we'll remember that. Now the question is, if binding energy is more, does it mean that our nucleus is more stable? Because binding energy we define as energy that binds nucleus together. So if there is more energy, does it mean that more stable is the nucleus? Answer is yes. Absolutely. No doubt about that. Okay. So if suppose two elements are there, or rather single element is there, or you say that same elements, two particles we are taking. Okay. Suppose that this is one element here, this is one element, this is another element. Same element X, and this is X. Same number of protons, same number of neutrons, everything is same. But in this one, binding energy is 100, and this one binding energy is 95. Which is more stable? Say first one. Suppose binding energy is more, it is more stable. Okay. So binding energy more means more stability. Yes. If you are going to talk about the same element. Same element. Okay. If binding energy is more, does it mean that the energy of the nucleus is less? Binding energy means what? Binding energy is because of the mass defect. How much mass defect has taken place? If more is the mass defect, we will say that more is the binding energy. Correct or not? But nucleus energy, if I talk, the total energy is what? Energy of the nucleus plus binding energy, because binding energy is actually released. Okay, and nucleus energy which is there with the nucleus. So total energy is what? Nucleus energy plus binding energy, that is the total energy involved in the process. So if binding energy is more, energy of nucleus will be less. So less the energy of the nucleus, more stable is the nucleus. Remember always, we always say that whenever you want the stability, your potential energy should be the least. Okay, so when nucleus energy is less, it is more stable. Same way, binding energy is more, it is more stable. Binding energy is more, nucleus energy is less. Stability. Remember. Okay. Now let's come out to another criteria, which is binding energy per nucleon. Binding energy per nucleon. So if we say that again there are two elements. Okay, there are two elements. Okay. Mass number of this, let's say, is 25 and its binding energy is 1000. Okay. 1000 what shall we say? Joule. Okay. Another element is there. Its binding energy is 200 or 400, but its mass number is 2. Now the question is, which is more stable? Since the binding energy is more here, so this should be more stable. But this is the binding energy for how many nucleons? 25. So on each nucleon, how much energy is there to bind it? 1000 by 25. That means 40 joule. Here, this is 400 joule, but it is on two elements only. So here binding energy per nucleon is 200. Here how much? 40. So which is more stable? So for stability, you require more binding energy per nucleon, not binding energy alone. Here we said binding energy is more because we said same element. X, same element is there. In this one I said this is binding energy 100, this is binding energy 95, so this is more stable than this one. Absolutely fine. Same element, but these are two different elements. Here this is having more binding energy, but here more nucleons are also there. So binding energy per nucleon is where? More. Here. So which is more stable? Okay, this one is more stable. If I say that this element is Y and this element is X, then Y is more stable than X. Okay, so which one is more influential factor? Binding energy or binding energy per nucleon? Binding energy per nucleon. This is more. Clear? Packing fraction. Now packing fraction is also a very similar term. Mass defect per unit mass number. So if more mass defect is there, that means more binding energy will become. So if mass defect is more, that means again it will be more stable. Similar thing only. No? So packing fraction is mass defect. Mass defect per unit mass number. Mass defect is more, binding energy is more. Binding energy per nucleon per unit mass number is more, means that means more stable. So more or less same kind of thing. Okay. Another criteria is here, that is N by P. What is this N by P? N by P ratio. Number of neutrons to number of protons ratio. Number of neutrons to number of protons. If it's almost 1 or very nearly 1, then the nucleus is stable. Okay. If N by P is almost 1, then nucleus is stable. If it is not, then nucleus try to be stable. If neutrons are more, neutrons will convert into proton to achieve the stability. If protons are more, protons try to convert into neutron. But that process comes under radioactivity, so we are not discussing. But this is what happens. Okay, so they always try to have N by P ratio equal to 1 so that they can achieve stability. Stability means less potential energy, less nucleus energy. more binding energy, right? Okay, just a moment. Right. Okay, so what next? Okay, next is binding energy per nucleon and mass number graph. Okay, binding energy per nucleon to mass number graph. Now in this one, what we can see, when we start from here, from the initial numbers, as you see that binding energy per nucleon is increasing. But this all is unstable region. Still binding energy per nucleon is very less in this. Okay, now in this one you see these peaks. There are certain peaks given in this. Where are the peaks? See, 2He4, helium. This table. Okay, same way you can see here oxygen. This is in peak, carbon. So these are relatively stable. But the maximum stability is in this region. Here, this is stability region. And iron is most stable. Okay, so this, if I say this is more stable, these are heavier elements. These are also unstable. Okay, so this heavier side elements are there. In this one, nuclear fission happens. Okay, they break. These heavier elements break into two lighter elements so that they can come to this side. They can achieve the stability. Exactly same way this side, these lighter nuclei. Okay, here what happens? Fusion. Okay, 1 plus 1, one element plus one element will be added so that they can go to this side. They can go to close to this. Okay, so here nuclear fusion happens, whereas here nuclear fission happens so that they can go towards the stability region. Okay, right? Nuclear force, strongest force we say, right? Short range force, strongest force. And this is one of the reason why in nucleons we can have so many number of protons, because we all know that protons means positive charge and there is strong electrostatic force of repulsion between them, but still they are inside nucleus. So there is some force which is binding them, and this is the force. And this is the force which is independent of the charge. That means this is the force between proton and proton also, neutron and proton also, and neutron and neutron also. Okay, so if suppose we talk about, we have a proton and proton inside nucleus. We are talking inside nucleus. Okay, neutron and neutron, and neutron and proton. A net force on which two pairs is more. So what happens on proton and proton? We know that on this one electrostatic force is active, and there is nuclear force active. So if I have to find what is the net force on this one, the net force on this one is going to be Fn minus Fp. Force due to nuclear force should be more than electrostatic force, then only it can be here. Otherwise, it will run away. Okay, so Fn has to be more. Between neutron and neutron, there is only one force, nuclear force. So in this one, net force is Fn alone. Here, N and P, nuclear force alone. So sometimes this question is also asked from you about net force. So we say that force between neutron and proton is equal to force between neutron and neutron is greater than the force, net force between proton and proton. Okay, what I am writing? Force between neutron and neutron is equal to force between neutron and proton is greater than force between proton and proton inside nucleus, remember. Alright, now the question, one more question is arises, this is nuclear force's attraction always? Answer is no. Answer is no. It can be repulsive also. When it can be repulsive? It depends on separation between two nucleons. Okay, so if suppose we say R is greater or equal to 0.8, Fm, Fermi. Then it's attraction force. But if R is less than 0.8, then it becomes repulsive. And if R is around 0.4 Fermi, not meter, Fermi, then it's huge magnitude, repulsive force of huge magnitude. Okay, large repulsive force. Large repulsive force. Fermi means 10 to the power minus 15. Okay, so this is how it is. This is what we know about nuclear force as such. Okay, and what is the range of our nucleus also? Nucleus radius is also 10 to the power minus 15 meter range only, Fermi. Okay, so alright, this is about our nuclear force. Okay, then what else we have? Okay, there are some numericals we have. Fine. So see then here what it is there, an element X and element Y are combining to make an element Z. Binding energy of X is 10 MeV, binding energy of Y is 15 MeV, binding energy of Z we have to find. And how much is energy released, that also is given to us. Okay, so shall we do? The solution says what is happening here, two elements are coming together to make one. So why two elements come together to make one? Because they want to increase their binding energy per nucleon. They want to go towards stability. Okay, so we will say that binding energy per nucleon of Z definitely is more than X and Y. Okay, all right. Okay, so binding energy of X plus binding energy of Y minus binding energy of Z must be equal to the Q released. Two elements are coming together to make one element. Okay, so what we have now here, we are saying this is 10, this is plus 15, this we are saying is minus binding energy of Z, and this is given to us as 3 MeV. Okay, correct only. But I told you that binding energy of Z is more than binding energy of two others. Correct or not? So what to do? I have written wrong there, because I have written this minus this subtraction. Yeah. So what it should be? It should be this minus and this plus. Now it's okay. So what is binding energy of Z? Binding energy of Z should be more. So it is 28 MeV. Okay, it is 28 MeV. Right? Then let's go for the next. Okay, this is binding energy per nucleon. So binding energy per nucleon for helium. How many nucleons are there? 4. Binding energy for hydrogen, 1 nucleon. Binding energy for hydrogen, there are 3 nucleons. What is the process? In a process, 1H1 plus 1H3 is 2He4. Whose binding energy will be more? Okay. So how much energy is released this time? Okay, fine, no problem to us. So what you'll write? What will be the solution saying? Solution says that binding energy of helium minus this. Okay. So binding energy of helium minus binding energy of, what is that? Hydrogen. Okay, binding energy of hydrogen 1H1 minus binding energy of 1H3 is equal to energy released. So binding energy of helium is how much? 4 elements, 4 nucleons are there. So 4 into 12. 4 into 12. minus 20 minus 3 elements are there, 3 nucleons, and this is 30. 3 into 30 the energy release. So how much? 48 minus 20 minus 90. It seems to be the opposite way it is. Their energy seems to be more than the energy of final product. So that means this requires energy. It's not an exothermic reaction, it's an endothermic reaction. Okay. So energy is required. How much? This is 110, 110, this 62, I think 62. Okay, MeV is the energy we require. Right? Correct or not? Because here this is the binding energy, this is the binding energy, and here binding energy seems to be 12. In fact, the values I have taken like this only. This seems to be more stable than this. Correct or not? Here binding energy per nucleon is only 12, whereas here is 20, and here it's less. Here is 10. No, per nucleon this is right. Yeah. So here is 30. Correct. Total energy here is 12 per nucleon. This is 20, and these two are more stable than this one. So the values taken are wrong. That's why answer is also coming minus 62 MeV. Okay. How it should be actually? So what we could have done, if I change this question, suppose I change this one and this one here. Okay. What we can do is 1H1 we can say suppose 8 MeV. Okay. And this 1H3 we say 5. Now it will come correct. Correct. Now we will get the correct answer. So now this is over already. Okay. Now change. Now what it is? This is 12 into 4, that is 48, minus binding energy of this 8, minus 3 into 5, 15. Okay, so 48 minus 23, that is 25. 25 MeV is the energy. Okay, 25 MeV is energy released in the process. Correct? Clear? Okay, then again similar thing, A plus B equal to C, A plus B are coming together and C is formed. Mass of A 1.5 MU, AMU, MB is 3 AMU, MC is 0.5 AMU. What is the energy released in the process? Okay, fine. What is the solution? Solution says it is MA plus MB minus MC into C square, because it's given in AMU. What to do? Okay, or 931 you can do directly, because 1 AMU equal to 931, that also you can do. So instead of C square, 931 mega electron. Okay, so what it is? MA is 1.5, 1.5 plus 3, 4.5, 4.5 minus 0.5, so 4 AMU. So 4 into 931 MU. That's the answer. Okay, I'm considering them that these two are nucleons, and from these two nucleons, this is being formed. So this is basically a nucleus. Okay, maybe. Okay, so these two are coming together, subtraction, and this is what the binding energy is. If suppose I am considering them to be nucleons, or otherwise you consider them as energy release. So mass of reactant minus mass of product into. Okay, clear? Alright, same thing we did here also. It's also same. These two are coming together and making the final thing. Okay, so mass of reactant minus, no, this is energy, this is not mass. Okay, fine. Then nuclear fission. Nuclear fission means is a heavy nuclei is breaking into relatively two smaller nuclei. so that they can achieve the stability. Okay, so what the process is? This is 92U235. We call this fuel. Okay, this is slow moving neutron. Its speed should be less because this has to be absorbed by the nucleus. Which nucleus? Uranium. This has to be absorbed. Once it is absorbing, it becomes unstable inside and it breaks into barium and krypton. Okay, and then it releases 3 neutrons. Now these are fast moving neutrons. Fast moving neutrons. And this is the energy. So what now? This process we do in nuclear reactor. Okay, and there will be, this is a fuel, and once to start it, we bring this slow moving neutron, and after that we have to sustain the process after this with these neutrons on. But these are fast moving neutrons. So what we have to do? We have to slow them down. So what we use moderator. Moderator is there to slow the neutrons. And what is moderator? Heavy water. This is moderator. Slows neutron. Okay. Now because in this process there are 3 neutrons are coming. So there is a possibility that if suppose that many uranium nuclei are there, many 10 or 15 are there. So everyone is going for this process of fission. So how many neutrons will develop? Now the 45 will develop. And suppose that more uraniums are there, but we don't want them to be involved in the process, but these will go and hit them. So what will happen? It will become uncontrolled process like atom bomb, but we don't want them. So what we require? We require certain elements which can absorb them, which can decrease their presence. So for that we use control rods. These absorbs the neutrons. Absorbs neutrons. And then what? Then these are 2 things that we use for controlling the process. 200 MeV of energy, what we use with that? This we use to heat the water. Okay, make steam, and that steam will be kept on turbine, or we run turbine with this steam, and then we produce electricity. This is what happens in reactor. But there is also possibility that because radiations also are there, so we make the reactor with concrete. Okay, so that those reactions, those radiations do not come out. Okay, so this is entire process. Then finally cooling is required. So who does cooling? Cooling is also done by water. Okay, cooling is also done by water. So this is your nuclear fission process. Then we have one more, fusion. In fusion what happens? Lighter nuclei come together and make heavier nuclei. So here this is the process which takes place on the sun, and on the sun fusion takes place. Okay, so 4 hydrogen nuclei, right? What is this then? -1 E0. This is beta particle, negative beta. So 4 hydrogen, 4 beta becomes helium. Helium is stable. We all know that. Okay. Then 2 more betas comes. This is neutrino. Okay. And then 27 mega electron volt energy is produced. This is happening in nuclear fusion. Okay. And hydrogen bomb is based on fusion only. Okay. So this is all about nuclear physics that we have in our syllabus. Okay. That's all. Right. So this is your QR code. You can scan it so that whatever I have written can reach you. Right. So that's all from me. Bye bye.